we can study what is a moving coil galvanometer or MCG. Galvanometer is a device used to detect the presence of electric current. The working principle of moving coil galvanometer is when a current carrying conductor is placed in an external magnetic field, it experiences a torque. And the magnitude of torque depends on the strength of electric current, and we know torque tau equal to NIAB sin theta. Now, what is the construction of a moving coil galvanometer? Moving coil galvanometer, it consists of a rectangular coil of fine insulated copper wire wound on a light non-magnetic frame. So here it consists of, this represents rectangular coil. This black line represents the rectangular coil. This is actually the top view. So if rectangular coils, if it is viewed from the top, it appears as these wires. So this represents rectangular copper wire and it is wound on a light non-magnetic aluminum frame. There is a soft iron core. This represents a soft iron core and it is a cylindrical soft iron core. If it is from the top view, it appears as a circle. So this represents the cylindrical soft iron core. Now, so this is the cylindrical soft iron core over which wires are uniformly wound, and this is placed between the pole pieces of a strong magnet, concave pole pieces of a strong permanent magnet. Okay, so these two represent magnet, permanent magnet. The cylindrical soft iron core and the concave pole pieces of the magnet makes the magnetic field radial. So here the magnetic field, this represents radial magnetic field. Okay, concave pole means like this. So it represents the radial magnetic field along the radius. Magnetic field is acting along the radius. So from north direction to south direction. So it represents radial magnetic field. The motion of the coil is controlled by pair of hair springs of phosphor bronze. So these represent the spring. So a pair of phosphor bronze springs are there in the top region and in the bottom region, and the importance of phosphor bronze spring is it has high tensile strength and low torsional constant. What is torsional constant you will study in the next section. A light aluminium pointer, this is a light aluminium pointer attached to the coil, measures the deflection on the scale. So actually in a galvanometer used in the lab, we can see only this pointer and the scale. And if you, in the inner region, it consists of a cylindrical soft iron core over which wires are uniformly wound, and it is placed between the pole pieces of a strong electromagnet. This represents the concave pole pieces of a magnet, which provides radial magnetic field. There is a rectangular loop provided with two hair springs. It is placed between the pole pieces of the magnet. The hair springs are made up of phosphor bronze and it is provided one at the top and other at the bottom. It is provided with a cylindrical soft iron core. Rectangular loop along with the soft iron core is placed between the concave pole pieces of the magnet. There is a pointer which can slide over the scale. And the two ends of the phosphor bronze are connected to two terminals of the galvanometer. This is the construction of galvanometer. The importance of radial magnetic field is the direction of area vector and magnetic field are always perpendicular, so that the angle theta will always be 90 degree and hence torque will be maximum. And the working of moving coil galvanometer. Let I be the current flowing through the coil, A be the area of the coil, N be the number of turns of the coil, and B represents the magnetic field. So when current flows through the coil, what happens? It experiences a torque. So it is a rectangular loop. No? When a current carrying conductor or when a current carrying loop is placed in external magnetic field, we know that it experiences a torque. Similarly, this rectangular loop, when it is placed in external magnetic field, it also experiences a torque. Because of the torque, the rectangular loop begins to rotate. So torque experienced by the rectangular loop is tau equal to NIAB sin theta. Here theta is the angle between magnetic moment and magnetic field. Okay, magnetic moment and magnetic field. Since it is a radial magnetic field, theta is always 90 degree. So, since radial magnetic field, theta is 90 degree, and hence the torque experience is given by NIAB. That is the first equation. The torque experienced by the loop is given by tau equal to NIAB sin theta. Okay, so here since it is a radial magnetic field, theta is 90 degree, therefore torque is given by NIAB. That is the first equation. Because of the torque, the rectangular loop begins to rotate. So in addition to that, there is a restoring torque set up in the coil due to the elasticity of the spring. So there is a twisting torque experienced by the spring, and that twisting torque or restoring torque is given by tau equals to K phi, where phi is the angle of deflection. Okay, so there are two torque experienced by the loop, that is tau equal to NIAB, and the restoring torque or twisting torque tau equal to K phi, and phi is called angle of deflection, and K is a constant which is called a torsional constant. And we know torsional constant is less for or least for phosphor bronze. That is why phosphor bronze is used as the spring in MCG. Okay, so at equilibrium condition, this torque experienced by the loop and the restoring torque are equal. Okay, so at equilibrium condition, both can be equated. So at equilibrium position, the two torques can be equated. First equation is equal to second equation. Therefore, we can write NIAB is equal to K phi. NIAB is equal to K phi, and phi is equal to NAB divided by K into I. That means deflection is equal to NAB divided by K into I. NAB, N represents the number of turns, A represents the area of the coil, B represents the external magnetic field applied, K is called a torsional constant. So this represents a constant, no? Therefore phi is directly proportional to I. So deflection is directly proportional to current. So as current increases, what happens to deflection? Deflection or the pointer reading increases. Okay, so here in the figure, as current increases, what happens to the pointer reading? Pointer reading increases or deflection increases. Thus we can say that deflection is directly proportional to the current flowing through the coil. Okay, so in a galvanometer, as the amount of current increases, what happens to deflection? Deflection also increases. So this is the working and the theory and working of a moving coil galvanometer. Now we can study what is the sensitivity of a galvanometer. A galvanometer is said to be sensitive if it shows large scale deflection even when a small current is passed through it. There are two types of sensitivity. First one, current sensitivity, and number two, voltage sensitivity. Then number one, current sensitivity. Current sensitivity is defined as deflection produced in a galvanometer when unit current flows through it. We have phi equal to NAB by K into I. This phi by I is called a current sensitivity. Phi by I equal to NAB divided by K, and this is called current sensitivity. Second type of sensitivity of the galvanometer is voltage sensitivity. Voltage sensitivity is defined as deflection produced in the galvanometer when unit potential difference is applied across its end. We have phi equal to NAB divided by K into I, isn't it? Now we can write I is equal to NAB by K into I is equal to V divided by R, isn't it? So phi by V, this is called voltage sensitivity, deflection per unit voltage. Phi by V equals NAB divided by KR, and this is called voltage sensitivity. We know current sensitivity is phi by I, that is given by NAB by K, and voltage sensitivity is given by phi by V equal to NAB divided by KR. Thus current sensitivity is given by phi by I equal to NAB by K, and voltage sensitivity is given by NAB by KR. If area doubles or area changes, both current and voltage sensitivity changes. If magnetic field changes, means both current and voltage sensitivity changes. If torsional constant varies, both current and voltage sensitivity varies. Okay. Now what happens if number of turns doubles? If number of turns doubles, number of turns of the coil doubles, what happens to length? Number of turns increases means length of the wire or length of the coil also increases. So number of turns double means length of the wire or length of the coil increases, isn't it? So if length increases, what happens to resistance? Resistance also doubles. So number of turns doubles, resistance also doubles. Hence, what happens to current sensitivity and voltage sensitivity? Current sensitivity is given by NAB divided by K, isn't it? So if current number of turns doubles means current sensitivity becomes 2NAB divided by K. That means current sensitivity doubles, isn't it? Similarly, what happens to voltage sensitivity? If number of turns doubles, we have voltage sensitivity is NAB divided by KR. If number of turns doubles means N becomes 2N. Then resistance also doubles, isn't it? So K into 2R. So 2 can cancel and voltage sensitivity is given by NAB divided by KR. That means voltage sensitivity remains constant, no change. So if number of turns doubles, current sensitivity doubles, but voltage sensitivity remains unchanged. Hence we can say increasing the current sensitivity may not necessarily increase the voltage sensitivity. If number of turns doubles, current sensitivity doubles but voltage sensitivity remains constant. Hence we can say increasing the current sensitivity may not necessarily increase the voltage sensitivity. So this is a very, very important point. Okay. Galvanometer is a device used to detect the presence of electric current. We can convert a galvanometer into an ammeter and also into an voltmeter. First we can study the conversion of galvanometer into an ammeter. We know ammeter is a device used to measure electric current, isn't it? And usually an ideal ammeter has zero resistance and normally the commonly used ammeter has very small effective resistance. So how will you convert a galvanometer into an ammeter? By reducing the resistance, isn't it? So resistance can be reduced by connecting a small resistance in parallel with the galvanometer. If a small resistance is connected in parallel with the galvanometer, it becomes an ammeter. Correct? The resistance connected in this way is called a shunt resistance. Okay, so shunt means resistance connected parallel to the galvanometer is called shunt resistance. So this is the method of converting galvanometer into an ammeter. So let I be the current. I be the current which is to be measured using a ammeter, and G represents the galvanometer, S represents the shunt resistance which is connected parallel to the galvanometer. So this arrangement becomes an ammeter. This is called an ammeter. So I be the total current which can be measured by using an ammeter, and Ig be the current flowing through the galvanometer, and this current is the current gives the full scale deflection for the galvanometer, and the remaining current I minus Ig is the current flowing through the shunt resistance. Okay, so I be the total current, I be the required current range of the ammeter, S be the shunt resistance. So at the point current divides into Ig and I minus Ig. And this whole arrangement, galvanometer and shunt resistance in connected in parallel, that forms an ammeter. So here galvanometer and the shunt resistance connected in parallel, this arrangement forms an ammeter. Now if two devices are connected in parallel, we know that voltage remains same, isn't it? So what is the potential difference across the galvanometer? Let G is the resistance of the galvanometer. Okay, G represents the resistance of the galvanometer. So what is the potential difference across the galvanometer? Current into resistance, that is Ig into G, isn't it? What is the potential difference across the shunt resistance? I minus Ig into S. So now potential difference across the galvanometer equal to potential difference across the shunt. Therefore we can write IgG, that is the potential difference across the galvanometer. Potential difference across the shunt is I minus Ig into S. Hence the shunt resistance to be connected in parallel is given by IgG divided by I minus Ig. Clear? So shunt resistance which should be connected in parallel so that a galvanometer becomes an ammeter is given by IgG divided by I minus Ig. So here G represents the resistance of the galvanometer, Ig is the current which galvanometer gives full scale deflection, I represents the current measured using an ammeter, and S is the shunt resistance. Okay, so this is the method of converting a galvanometer into an ammeter. Now we can study the conversion of galvanometer into an voltmeter. Voltmeter is a device used to measure the potential difference across 2 points in a circuit. An ideal voltmeter should have infinitely high resistance, and the voltmeter normally used should have high resistance, very high resistance. So how will you convert a galvanometer into a voltmeter? We can increase the resistance, no, isn't it? Galvanometer has some resistance, and in order to convert galvanometer to a voltmeter, we should increase the resistance. How the resistance is increased? By connecting a very high resistance in series to the galvanometer. Okay. Hence, a galvanometer can be converted to a voltmeter by connecting a high resistance in series with it. So, this is a galvanometer. This is the high resistance which is connected in series with the galvanometer. So, whole arrangement becomes a voltmeter. This becomes a voltmeter. Let Ig be the current which galvanometer gives the full scale deflection. G be the resistance of the galvanometer, and R is the high resistance which is connected in series. And V represents, or 0 to V represents the voltage range of the voltmeter. So, voltage that can be measured by using a voltmeter, let it be V. So, here G represents the galvanometer resistance, Ig is the current for the full scale deflection, V is the voltage measured using voltmeter, and R is the resistance connected in series. According to the figure, G is the galvanometer resistance and R is the resistance connected in series. Here we can write from Ohm's law, we can write V equal to Ig into G plus R, isn't it? Total voltage is equal to current into total resistance. Here what is the total resistance? G plus R. So, we can write V equals Ig into G plus R. So, directly we can write V equals Ig into G plus R. Clear? Now, V by Ig can be written as V by Ig is equal to G plus R, and the resistance to be connected in series is given by V by Ig minus G. So, from this formula we can find out the resistance to be connected in series. Clear? So, R equal to V by Ig minus G, and if you connect this resistance in series with the galvanometer, it becomes a voltmeter. Okay, children? Now, we can do a numerical relating conversion of galvanometer to voltmeter. The question is, a galvanometer coil has resistance 12 ohm and the meter shows full scale deflection for a current of 3 milliampere. How will you convert the meter into a voltmeter of range 0 to 18 volt? So, how will you convert galvanometer to voltmeter? By connecting a high resistance in series, and the value of high resistance is given by R equal V by Ig minus G. This is the formula, and we know V equal to, what is V? 18 volt. 0 to 18 volt is the range given, we can take the higher value 18 volt. And what is Ig? Ig is the current for the full scale deflection which is given as 3 milliampere. So, 3 milliampere convert to ampere, 3 into 10 raised to minus 3. Clear? Now, what is the galvanometer resistance? Capital G, it is 12 ohm. So, capital G is equal to 12 ohm. All the values are given, so we can directly substitute. Therefore, R equal to 18 divided by Ig. Ig means 3 into 10 raised to minus 3 minus capital G, which is 12. Okay. So, it is 18 divided by 3, 6 into 10 raised to 3, 6000 minus 12, that is 5988 ohm. So, this much resistance should be connected in series, that is the final answer. So, 5988 ohm should be connected in series. Should be connected in series with the galvanometer. Okay. Now, one more question relating conversion. A galvanometer has a resistance of 15 ohm and the meter shows full scale deflection for a current of 4 milliampere. How will you convert this meter into an ammeter of range 0 to 6 ampere? So we know that a galvanometer can be converted to ammeter by connecting a low resistance in parallel. That means that by connecting a shunt resistance, isn't it? And what is the value of the resistance connected in parallel? S is equal to, we have the formula IgG divided by I minus Ig. That's a direct formula. Now, what is Ig? Current for the full scale deflection is given as 4 milliampere, isn't it? 4 milliampere we can convert to ampere, 4 into 10 raised to minus 3 ampere. Now, what is the galvanometer resistance given? Galvanometer resistance is 15 ohm. So, we can substitute 15 ohm. Okay, now what is the current? We have to convert galvanometer into an ammeter of range 0 to 6 ampere. So, current is equal to 6 ampere. Okay, now what is the shunt resistance value? S is equal to Ig. Substitute 4 into 10 raised to minus 3 into capital G. Capital G is equal to 15 divided by I minus Ig. That means 6 minus 4 into 10 raised to minus 3. So 15 into 4, that is 60 into 10 raised to minus 3 divided by 6 minus 4 into 10 raised to minus 3. That means 6 minus 0.004, isn't it? So the answer is 5.996. 5.996 can be approximately taken as 6. So 60 into 10 raised to minus 3 divided by 6, that is 10 into 10 raised to minus 3. Okay. So the shunt resistance to be connected in parallel is given by 10 milli ohm, we can write. Okay. So this much resistance to be connected should be connected in parallel. So 10 milli ohm, this resistance should be connected in parallel to the galvanometer. So in order to convert galvanometer to an ammeter, this much resistance should be connected in parallel. Okay children.